let's do another example here. So here I just want to make sure that you guys understand to just sort of like cross off or erase the 2 that was in front of the x plus 1 here in the second piece. So I apologize about the 2 typos in this lesson here. Okay, so here what I want to do now is answer the first part where I'm trying to figure out, is g continuous at x equals 1? So I need to first ask myself, is g defined at x equals 1? So g of 1 is equal to, and now I want to plug it into this function, right? Because I have that x is greater than or equal to 1. When x is greater than or equal to 1, we use the piece x plus 1. So now I have 1 plus 1, which gives me 2. Okay, and so we've satisfied the first condition, right, for continuity because g of 1 is a number. Okay. So now I need to check, does the limit as x approaches 1 of the function exist? So I need to consider the limit as x approaches 1 from the left of the function, and then the limit as x approaches 1 from the right of the function. Okay, and that's because the piecewise function is switching from one piece to the other at x equals 1, right? So from the left, I want to be using the top function, right? So this is the limit as x approaches 1 from the left of negative x squared plus 4. So this gives me negative 2 and then 1 squared plus 4, which gives me 2. Okay, now let's consider the limit as x approaches 1 from the right of the function. So now I'm going to be using the bottom piece, and when I plug in, I get 1 plus 1, which is 2. Okay, so the limit does exist, right, because the left-hand limit equals the right-handed limit. So the limit as x approaches 1 of g of x is equal to 2. All right, and so now the third condition is that g of 1 must equal the limit as x approaches 1 of g of x, which it does. So the limit as x approaches 1 of g of x is equal to g of 1, which is 2. Okay, so all 3 conditions are satisfied. So the answer here is yes. Okay, g is continuous at x equals 1. So by definition of continuity. Okay, so now that we have continuity, I need to remember that continuity does not, and I repeat, does not imply differentiability. Okay, so if I know the function is differentiable, then I can say it's continuous. But I cannot say the function is differentiable based on the fact that it's continuous. All right, so continuity does not imply differentiability. So we do need to actually check if the function is differentiable at x equals 1. All right, using what I said on the first page of notes here. So what I'm going to do is I'm going to consider the left-hand and right-handed limits with the limit definition of the derivative here. So I'm going to consider, right, and that's, again, I'm considering the left and right-handed limits because the function is changing, going from one piece to the other at x equals 1. So I'm going to set up these limits. So I'm going to say the limit as x approaches 1 from the left of g of x minus g of 1 over x minus 1. So I need to compute that limit, and then I need to compute the limit as x approaches 1 from the right of g of x minus g of 1 all over x minus 1. Okay, and so now what piece of the function should I use for the limit from the left? So I should be using this piece, right? Okay, so now wherever I see g of x, just like I was doing when I was checking for continuity, I'm going to replace it with negative 2x squared plus 4. So this is the limit as x approaches 1 from the left of negative 2x squared plus 4. Okay, minus, and then now I go back up to where I found g of 1 from part A, which was 2. Okay, so here, if you want to just see side note here, g of 1 is equal to 2. Okay, so that's where I was getting that from. I was just plugging in g of x and g of 1. So maybe it might be helpful if you see me highlight what I was doing. And then this is my g of 1. Okay. And I'm probably going to need more room here. So now, when I combine like terms here, I get that this is the limit as x approaches 1 from the left of negative 2x squared plus 2 over x minus 1. And if you tried to plug in here, you would, in fact, get the indeterminate form 0 over 0. So what we did here, right, is we would try to factor and then produce cancellation. So we need to factor the numerator. So this is going to be equal to the limit as x approaches 1 from the left. Now look at the numerator. They both have a 2 in common, correct? But what you want to do is factor out that negative as well, okay, because I don't want that x squared term to be negative. So I'm going to have negative 2 and then x squared minus 1 all over x minus 1. Okay, because the term here, the plus 2, so referring to over here, this plus 2 becomes a minus, right, when I factor out the negative. Okay, and just to double make sure that you understand the factoring, you can just distribute it back out and confirm that you get back to where we started. Okay. So now we can factor further, right? Because in the numerator, x squared minus 1, that's the difference of squares. So we're not quite done factoring. So this is negative 2 x plus 1 times x minus 1 all over x minus 1. And now you should see cancellation here. And so once we cancel, we get negative 2 times x plus 1. And then plugging in, we get negative 2 times 1 plus 1, which is negative 4. Okay, so for the limit from the left, considering the left-handed limit, I get that it's negative 4. Okay, so now we'll consider the right-handed limit. But in this case, I'm not going to use the same g of x, right? Because I'm approaching 1 from the right. So if I'm approaching 1 from the right, I'm going to be using the bottom one instead, right? I'm going to be using this one. So when I go to plug in for f of x, I need to be using x plus 1. So I'm going to get that this is the limit as x approaches 1 from the right of x plus 1 minus 2 all over x minus 1. Okay, so I did in fact just plug in g of 1. That's where I got this 2. And I'll use a different color here because we were different. In this case, the g of x, we're using the bottom piece because we're approaching 1 from the right. Okay, so now simplifying the numerator here, I get that this is x minus 1 over x minus 1. Okay, but x minus 1 divided by x minus 1, that just becomes 1. Right, you could say that the x minus 1's cancel, or just remember that a quantity divided by the same quantity is just 1. Alright, so even though it looks like some crazy stuff divided by some crazy stuff, as long as that crazy stuff's the same in both the numerator and denominator, that is in fact just 1. So this is the limit as x approaches 1 from the right of 1, which is 1. Okay. so now what do you notice here? The left-handed limit does not equal the right-handed limit, right? And so since the left and right are not equal, the function is not differentiable at x equals 1. So since the limit as x approaches 1 from the left of g of x minus g of 1 over x minus 1 does not equal the limit as x approaches 1 from the right of g of x minus g of 1 over x minus 1, then g is not differentiable at x equals 1. Okay, so the last thing I did want to mention here, so that's why I included part C in this. Alright, so now I'm asking you, is the function differentiable at x equals 2? Okay, so I'm asking it to you at a different x value, right? In part B, we're talking about at x equals 1, and part C, we're talking about at x equals 2. Okay, so now I'm going to go back up to the original function, right? And so it says that for all x values greater than or equal to 1, I'm using this piece of the function x plus 1. So I don't, in this case, need to consider the left-handed, right-handed limits for the limit definition of the derivative. I just need to use the limit definition of the derivative to figure out whether or not g is differentiable at x equals 2. So what I'm going to do is I'm just going to compute the limit as x approaches 2, g of x minus g of 2 over x minus 2. Okay, so again, I don't need to consider the left-handed and right-handed limits in this case because I'm not switching from one piece to the other at x equals 2, because in fact, for all x values greater than or equal to 1, I'm just using this bottom piece here. Okay. So now what I'm going to do is just plug in x plus 1 in for g of x in my limit definition of the derivative. And then I need to just compute what g of 2 is. And again, I'm plugging in 2 into the bottom piece, right, because of how it's defined here. So I need to say that this is the limit as x approaches 2 of x plus 1 minus, and then g of 2 is equal to 2 plus 1, which is 3. And then this is all over x minus 2. Okay, so here I just plugged in g of 2. And then I plugged in g of x. Okay, and then again, g of 2, I just plugged in 2 into x plus 1. So going back up here, I just plugged in 2 into this piece, into this bottom one. Okay, and then now when I simplify, right, I'm just going to get that this is the limit as x approaches 2 of x minus 2 divided by x minus 2. And so, again, like we said before, this is just going to be 1, which is 1. Okay, so since the limit exists, right? Limit as x approaches 2, g of x minus g of 2 over x minus 2 equals equals 1. Then g is differentiable at x equals 2. In fact, g prime of 2, or the derivative at 2, is 1 by definition. Okay,